Okay, good morning, good afternoon, everybody. In today's presentation, I'll present the construction of the Allotrope simple model, the ASM, and using a JSON schema for validation, all of this to achieve data interoperability. So let's start with a brief overview of the ASM. The ASM, which is a simple text representation of the Allotrope tabular model, is using JSON as its underlying syntax for data presentation. It uses the terms from the AFO, from the Allotrope Foundation ontology, and it leverages the ADM that were already defined by the subject matter experts, as George described in the modeling working group. And when I mean it leverages the ADM, it means that we will see how it's generated from the ADM, and then we get the ASM. So a pre-existing condition for the generation of the ASM, it's the definition of an ADM, the Allotrope data model. Now, when we are talking about tabular models, the Allotrope tabular models applies to domains where there is a single business object being measured, and all the measurements are directly related to this particular object. And a simple example is the result of an experiment. And like we are using in the ADM case, we are using a shackle for validation. In JSON, we have a technology which is called a JSON schema, then that the ASM is utilizes for a description and the validation of the data. Why did we pick JSON? And we heard a lot of requests for simplicity. So with JSON, we are minimizing the verbosity of the code. The machine can parse it very fast. There is a cross-platform way to represent the data, whether you are on Linux, whether you are on Windows. It's a complete interoperable way to data exchange. The term representation for a business reader and for a coder is similar. It's very intuitive. Key value pairs, very intuitive, as we'll see in a moment. There is an extensive off-the-shelf tooling to support almost in every language. So for example, when we'll see our validator, we just pick it off the shelf, an online validator, and we didn't develop, like in the case of the shackle validator that we had to develop here, we're using off-the-shelf tools. You have it in any language, whether it's Python, Java, C#. And it's widely used to deliver and exchange data using REST, which is a client-server architecture for the web to achieve a scalability in a distributed architecture of the internet. There are some limitations of what you can model within a JSON object, but this limitation is you can look at it in a positive way, which makes the code more predictable, easy to read, and much simpler. So as we said, we are using the ASM to model the tabular use case of our use cases. And the JSON object format, which is a collection of name value pairs, it aligns very well with the structure of the tabular model, which is a key value pair. And then the aggregation model is an extension of our tabular model, which allows aggregation of data attribute under a unified context or index collection of similar data pattern. And when we look in a tabular models, and this is an example of an aggregation model, it's a set of key value pairs. In this case, we have a pick list, and the pick list is indexed. So we have pick 1, pick 2, pick 3, etc. And this is a collection of index of picks. And now we have different facets for every pick. So we have like description and retention time. So we are aggregating a different attribute with a similar pattern. So we have first layer of aggregation, which is an index of picks. And then we have second layer of aggregation of different facets: description, retention time, description, retention time. So it's a tree of aggregation that it's actually very easy to model using an Excel spreadsheet. And that's what, as George mentioned, we are using in the modeling working group. And it's very easy to represent this structure in a JSON format. So let's look, first of all, on our entire product line and compare the different life cycle of a data message from the instrument all the way to our database or our repository, going from the instrument through our different product line, and we'll understand the life cycle of a data packet. So we start with an instrument where let's assume that the vendor produces the experiment result in a proprietary file format in proprietary term. So first of all, we need to do the data acquisition. And the data acquisition can be, there are different architecture, it can be push or pull. If it's pushed, it's initiated by the instrument itself. If it's pulled, by the enterprise IT system. And we might have a publication subscription, which is a producer and consumer. We might have an IoT for acquisition, like OPC UA. We might have an information highway exchange, like the enterprise service bus. And practically, there are different architecture within our IT system to do the data acquisition. Once we have the data acquisition, we are getting the proprietary format that we need to map it to our standard ontology and standard terminology to bring different results from different devices, from different vendors into a common ontology and common terminology. So in this example, we see the conductivity results in the Excel spreadsheet. And it's a very simple, just to have the idea, measurement identifier, measurement time, analyst, sample identifier, equipment serial number, batch identifier, conductivity, and temperature. Those are the different parameters that we would like to map to the Allotrope preferred label. The Allotrope preferred label, which is the preferred terminology in our AFO, in our ontology. And it might be that there is vendor A, vendor B, vendor C. So for example, if vendor B produces for timing the time of measure, and vendor C produces his terminology is time, we need to map it to measurement time, which is our preferred label in our ontology. And for this, to perform this terminology, we have a new project. It's very early in the process, which is called ATM, Allotrope Terminology Mapping, where it will be practically a library of mapping from vendor-specific instrument to our Allotrope terminology. Once we map and we now can compare different devices, but it's instead of apple and oranges, it's all about the same terms, whether it's coming from instrument A or B. Now we can structure the data into the ADM, into a structural message. And until now, we structure it with using RDF. So here we see the conductivity, because it's a tabular model. We see all the terms that I described earlier, the temperature, the conductivity. So we structure it within the ADM using a rich data format, RDF, and then we can containerize it within an ADF file. And now with the ADM file, we have the ADM in the data description. And in the case of like qPCR, which has data cube information, or HPLC, the multi-dimensional array, we put the data in the data cube. If we have related files that we want to include in our repository, like the raw information of the instrument, we have a virtual virtual storage, which is the data package, and it's all containerized within a single file, the ADF, and it can go into our archival system or for other usage in the storage. So this is the classical way that things were done until today. Before I'm talking about the alternative, we can also unpack, if we want to load it into our enterprise database or data lake or knowledge graph, whether it's a label property graph or triple store, we need to unpack the ADF using the ADF library in C# or Java, and then we can load it into our enterprise database or knowledge graph or triple store, depends on your choice. So as I said earlier, now we have an alternative way for tabular model to load the information that is coming from the device into our enterprise data system or into our storage, which is after the mapping, we are structuring the information in a JSON format using the ASM. So here we see the same information of the conductivity experiments. The same, it's not exactly the ASM. We'll see in a moment what is an ASM, but it's almost identical. So we have the same line items as we saw in the Excel worksheet, measurement time, and the time, it's key value pairs, measurement identifier, analyst sample identifier, and two of the results, conductivity, value, unit, temperature 28.6, and degree Celsius. So it's very simple, very well understood, very easy to read, both for the coder and to the business user. And from the ASM, we can load the document either in an object store or a database, or store it in a storage as a .json file. If we want to containerize it, in the case of ASM, we are not mandating any type of container, but recommending using zip. So you can zip it with the JSON document with any type of file that you wish, typically the original raw format that came out from the instrument. And so you can zip it and store it in your enterprise storage system. And a simpler alternative for integration in the case of ADF is that the vendor outputting the ADF natively, and that's for any model, whether it's graph or tabular model. So bypassing all those stages that we need to do ourselves or by a solution provider. So having the ADF produce directly from the instrument itself, so producing the ADF file. But what more makes sense in the case of ASM is using REST API, and we'll have an example, and there was a question about it earlier. REST API, it's a typical way for carrying a payload of a JSON format. So vendor outputting the ASM natively as a REST interface for tabular and aggregation model. And there is no reason why in now age, an instrument will issue the results in a CSV or in PDF and not as a REST client, sending it in a client-server architecture to any kind of a web service that exists in our enterprise system. So let's look a very brief demo. What is an ASM? So I'll start with the actual table that is coming from the modeling working group, and we'll do it for the connectivity. So this is what the modeling working group is doing. They're modeling the ADM within a spreadsheet. So we have here the parameter type, the parameter itself, the preferred label, and the unit system, and an example of a real instance. So we have our 8 parameters, the measurement ID, operator, sample ID, and this is the preferred label, how we are unifying those terms with the AFO. Now, when translating or generating the ASM, what we take into consideration, and we'll see the conductivity to the relation to ADM later on, within the ASM, we take only the preferred label, the measurement identifier, the measurement time, the analyst, sample identifier, serial number, batch, conductivity, temperature, and the result. And we model it, we insert it in a JSON format. So let's look at the ASM that is representing this data instance. So we see the comparison between the two. This is the actual ASM. There are two lines that we'll talk in a moment, but as you see, the table that describes the result of conductivity is now described in an ASM JSON message. So measurement identifier, very similar. Key value pair, measurement time, analyst, sample identifier, equipment serial number, one-to-one matching. And we have the conductivity, which is the value and unit, conductivity, value and unit, temperature, value and unit, temperature, 28.6 degrees Celsius, value and unit. There are two additional lines that we're adding to the ASM, two additional lines. Which one is a very easy to understand line, which is the comment. It's a generic comment that is just, you can describe whatever you want in this ASM message. So in this case, the comment is conductivity ASM, very intuitive. And the other one is the ASM manifest that gives us the relationship or the how do we achieve compatibility with the ADM. Within the manifest, we have all the information about the vocabulary that is used. It's actually identifying the actual ASM. It makes the connection with the validation, the JSON schema validation. So all the complexity is hidden in the ASM manifest, and the rest is very simple JSON format. So let's go back to our presentation. So we'll talk a little bit about REST API and the ASM, which is very natural for a REST interface to carry a JSON payload. So a REST representational state transfer protocol is an architectural style for providing standard way to do data exchange in a scalable way in a distributed fashion within system on the web. We can look at it using the REST and the JSON play as a major force for lab automation. The mechanism allows different subsystems to be used in our laboratory and within our organization, whether it's ERP systems, which are general in the organization, ELN, LIMS. Now you can exchange data in a way which is very standardized, very well documented, secured using HTTPS, and very much structured. It's using a RESTful API, and I don't need to preach about RESTful API that are using in the daily basic, but they are the basic in the internet for doing integration, interfacing between client and server, and to achieve interoperability. So with the ASM now, we can automate various functionalities within our subsystem in the organization. We can push or modify data using the REST push or post, and we can export data between different instrument and subsystem and integrate a lot of third-party application, a very easy integration between program, system, analytics. And I'm going to show a demo again about REST that is coming out of the box. So we'll have here, what we're going to show is that the conductivity ASM that we saw in a moment ago, the very simple conductivity ASM, is using a REST API to a conductivity meter, from a conductivity meter, and is using a post It's sending natively from the instrument an ASM experiment result into a Google Sheet, which is in a different location on the cloud, carrying the ASM as the payload. So we look at the Google Sheet, and I prepared here a Google Sheet. And I'll show you the simulator. Okay, we'll try to fit everything in one screen. And I'll delete the last few results. And now I have a simulator of it's working in a different location on the cloud, written in Python, that is actually producing ASM message, and each row in this spreadsheet is a JSON representation of the ASM, but broken into a spreadsheet in a table. So the key value pairs, the keys are is the column itself, and the value is the row of the ASM message. Now I'll set it up to 10 messages, each one in 1 second, and let's launch it. We see the messages are coming, ASM messages are coming one after the other directly from the ASM client, from the device itself. And we get 10 messages, and we see how simple it is using REST API and JSON structure to populate a different analytical and report system in the cloud. And actually, to create it, except of writing the simulator, coding the simulator, the rest was codeless solutions to get from the client to the Google spreadsheet on the network. So let's talk about how do we generate and how do we get compatibility between the ASM and the ADM. As we said, the ADM is prerequisite to the generation of the ASM. So first of all, we are, as Joe described, we are minting the different terms that are related to the instrument, and then we are modeling it in the modeling working group using the ADM, using the Excel spreadsheet, as you saw earlier. And for the last few months, we were working on the development of the ADM to ASM transformation tool, the ADM to ASM transformation tool. So the input to the transformation tool is the ADM itself that is described using Shackle, the RDF graph in turtle format using Shackle, and it is translated using the transformation tool to the ASM. This is a one-way transformation, and it will be done during the governance process. So on our on our GitLab repository, we will have, like we have all the different ADMs, we will have all the different ASMs that are related to the specific ADM. So having the ADM is a prerequisite to generating the ASM. And through the manifest that you saw earlier in the example, we are maintaining the compatibility, the relationship between the two using the same vocabulary and identifying the ASM. And actually, the tools that is transforming the ADM to ASM has the capability of doing the opposite from the ASM back to the ADM, and we can guarantee bidirectional compatibility. So let's understand it again. For the ADM, we have the Shackle file, in turtle format. We're using Shackle to describe and to validate an ADM data instance. So we are using shackle to validate the ADM data instance. So the input for the transformation is the shackle file that is related to a specific ADM. We generate using the transformation tool the ASM, and now we have JSON schema. We have JSON schema to validate the ASM data instance. The tool allows us, again, to do a transformation back to ADM with the availability of the manifest file. We achieved the compatibility, but again, this is for bidirectional compatibility verification, but the transformation is from the ADM to the ASM. So the technology that is used for validation of the JSON file is JSON schema, and we can find it on jasonschema.org. So the parallel to shackle in the case of RDF that we are using for the ADM, we have JSON schema for the case of JSON that we are using for ASM. And we'll see validation in a moment. This is how we maintain a model consistency and of the data in the semantic context between the ASM JSON and the ADM RDF. So let's look on ASM validation and let's see it in action. So what we are going to see, we're going to see a JSON schema validator that we just picked online. You can pick any JSON schema validator, but we picked up the one which is very fast, as you'll see it in a moment, from Newtonsoft. And the JSON schema validator evaluates a conformance of ASM data instance with a set of conditions and rules in the associated JSON schema. And we'll go deeper into JSON schema in the last presentation during the technical session. We will give a primer about JSON schema, but some hints I will give them today when I'll do in a minute the presentation. And you can find a lot of packages in different languages and validators and generators at the jasonschema.org. So practically the JSON schema validators has two inputs. One is the data instance, so the conductivity.json, which is the result of our experiment. And the other one is the conductivity schema JSON, which is the schema that is used to validate the data instance. So let's look at the brief demo. Let's start with so we have two boxes in this validator. Again, it's an online validator. One is the JSON schema itself, the input to the JSON schema, and the other one is the data instance, which in our case, it's the conductivity ASM. So just to give you an idea, and that's one example, if you remember when we modeled the ADM, let's look at this spreadsheet, there were three data instances, parameters that were required. The measurement time, it's required, the sample identifier, and the conductivity. The three of them are required. So actually in the JSON schema, we have a field that is called required as a key. It's a key value pair. And there are three parameters that it says that three properties that are required: measurement time, sample identifier, and conductivity. So let's see, currently everything is working, no errors, JSON validates against the schema. Let's erase the measurement time, and you'll see immediately that an error was found. Required properties are missing object measurement time. On the fly, we got it. Let's put it back. And let's play with the temperature. If you remember, the conductivity was required, but the temperature was not required. So let's erase the temperature. So even that I'm erasing, no error found because it wasn't required. So let's put it back. And now let's play with the values. So it makes sense that the temperature value is a numeric value, but let's try to put a string value. And I'm getting immediately an error, invalid type or invalid type, expected number, but got a string. So let's put it back. And now everything is validated and everything is correct. Let's look a little bit on a more complex schema, which is the qPCR. Without going into the qPCR, but the qPCR has data cubes. It has data cubes, so we see here a list of measurements. So in the case of ASM, we describe it as a list. The array is a list. And we see in the qPCR that there are a required field that has to exist within the JSON data instance. One of them is the well volume. So as you can see, there is a well volume here. So what I'll do, I'll erase all the well volume. And I'm getting immediately on the fly required property are missing from object well volume. Let's put it back. And let's play with the unit of the well volume. It's a microliter, and I'll change it to milliliter. And I'm getting immediately a message that my schema was violated since I don't have the microliter as unit for the well volume. So this is a brief demo of the validator. Again, we will go deeper in our technical session on the last day of the event. So to summarize it, the ASM, to understand the ASM, it's a very simple model of the tabular use cases. It's a self-described unique information parameter, which is actually the AFO, which is unique. The AFO term is unique within the ontology, and the value unit is a key value pair. A key value pair between the unit information and the value and the unit of the parameter. And it can be used for any of our tabular models, and both Ben and I will take questions at this point. Thank you very much.
Great, thank you.